little, I used to think that it would be the coolest thing in the world to have Coca-Cola for blood instead of blood. Imagine how awesome it'd be for you to have your favorite carbonated soda inside of you. Of course, it wasn't until I matured later on that I realized how painful that idea would actually be. Imagine having a highly pressurized can of soda, shaking it up and opening up all the contents and fly inside of it. All of that happening inside of your body, your head, your veins. That would be terrible. So when I was thinking about this soda blood idea, I started thinking it wouldn't make sense either way, because wouldn't that mean that I would have a heartburn every second? And wouldn't that mean that instead of a nosebleed, I'd have carbonated bubbles fizzing out of my nostrils? I was remembering this old soda blood idea of mine when it piqued my curiosity in fetal and embryonic development. I don't know. Which came first, the blood or the blood vessels? So today, that is what we're going to be talking about, and this is my current driving question. So to start things off, Hope Flores was a baby born in December of 2013, and she was delivered via an emergency C-section due to fetal maternal hemorrhaging, which is essentially a large loss of blood in a baby before its birth. So when the doctors delivered Hope Flores, they described her, quote, "she's ghost pale," and when pricked for a blood sample, get this, there was no blood that was drawn from the baby because it turned out that over 80% of her blood supply was drained in her mother's womb. Eventually, they had to do an emergency blood transfusion, and eventually she became healthy and she is alive today. So congratulations to Hope Flores. But why am I bringing this subject up to you? The first time I heard this story, it piqued a very simple but yet controversial question in my mind, and that was, if no blood was drawn from this baby's arm or her veins or arteries, doesn't that essentially mean that her blood vessels were empty? Doesn't that mean that there are hollowed out tubes of nothingness flowing in her, that when her heart is pumping, there's not essentially any blood pumping because there was no blood in the first place to begin with? So, with that being said, I think it's safe to assume that you can't have blood vessels without the blood, and you can't have blood without the blood vessels. So today we're going to go sort of delve into how blood and how the blood vessels form, which came first, even if there is a first. So first things first, in order to fully understand what we're going to be talking about, we should know what the term vessel means. Now I'm sure that when you all think of the term vessel, you think of some long elongated tube that transports one object from one place to another. But biologically in our body, what a vessel is a pathway blood uses to flow throughout our body, to circulate, to fill our lungs and to fill our body with oxygen and all the nutrients that we need. Now, there are 3 layers of the vessel, but the most important thing that I want to point out here is that the layers of the vessel don't form in orchestra with each other, but rather they form layer by layer. And so, the very first thing that we're going to talk about is endothelial stem cells. Now, it's a big word. I'm going to condense it for you to make it simple. So the first thing we should understand when talking about endothelial stem cells is, what in the world is a stem cell? So a stem cell essentially is a cell in your body that can turn into any type of cell. Tissue cells, nerve cells, liver cells, blood and immune system cells. I like to think of stem cells as, if you've watched X-Men, Mystique, because Mystique can turn into any type of human being, just like stem cells can turn into any type of cell, if you've ever watched X-Men. So endothelial stem cells are multipotent, meaning that they're stem cells that can branch into specific types of cells only. So they're more limited and they're less diverse, but if I were to take the stem cells of somewhere in the brain, heart, or bone marrows, then they can turn into specific type of cells only. However, embryonic stem cells, and remember when I'm talking about embryonic, I'm talking about embryos inside the mother's womb where the babies are developing. They're pluripotent, meaning that one stem cell in an embryonic stem cell can turn into any type of body living tissue. So that's like your brain, tissue, hair, blood cells, cardiac muscles, anything else. And what is so cool about endothelial stem cells is that, just like I said, how they relate to Mystique from X-Men, they can turn into any type of cell. These are actually the first layers of cells that are found in the first layer of a blood vessel. So to sort of simplify this, or give you sort of an analogy, if you've ever had a cut before, or a scrape on your knee, where blood just started gushing out and eventually healed, that is the reason, endothelial stem cells are the reason why that was happened. For example, in the 3rd grade, I was so excited to race the fastest person on our team, Charles Labange, and because I had been practicing for weeks, getting ready my stamina, getting ready to finish the race and win it. the day of the race, I had been so pumped up that I forgot to tie my shoelaces. So I ran, and I fell. And then before I knew it, my knee was covered in blood, and my face was covered in tears. Eventually, that wound healed up, and that blood started to clot, and it started to stop all the bleeding. But why does that happen? Endothelial stem cells are the reason, because Dr. Louis Ignero quotes, "Our bodies contain 6 trillion endothelial cells, which line 60,000 miles of blood vessels in a single layer." 60,000 miles of blood vessels in a single layer. So when that wound of mine healed up in the 3rd grade, when all the blood was gushing out, what happened was those endothelial cells allowed the new blood vessels to create when all the damaged parts of my skin had been broken. So it essentially created new vessels off pre-existing vessels. And this is a really cool process called, oh, sorry, I forgot to mention that you can sort of relate endothelial cells to lizard tails. Now, if you haven't heard or you don't really know about this, lizards, or specific types of lizards, can, when they feel hunted or when they feel in danger, they can actually cut or amputate their own tail off as a distraction for them to run away. What's really cool about this is that they can regrow their tail back once it's been cut off. And although we can't regrow a part of our limb if we cut it off, we do have something similar in that endothelial cells can create new blood vessels off pre-existing vessels whenever a part of our body is damaged or wounded. So, there we go. This is a process really cool called angiogenesis. And what angiogenesis is what I said before, the branching of new blood vessels from pre-existing ones. This happens every day in our lives. Whenever you have a cut, whenever you're bleeding and it stops and it heals, angiogenesis is someone you can thank every day of your life. It happens in embryonic development, and it happens in your everyday adulthood life. But one other thing that cannot happen in adulthood and can only happen in embryonic development is vasculogenesis. Now, why this is so important is because when I'm going to be talking about this, we're going to further delve into how, why, and what happens when your blood and your blood vessels start to form. So vasculogenesis is essentially the development of your vascular system, your blood vessels, your blood, and everything else. And a quote from Dr. Marcus Friediger states that the vasculature is the earliest organ to develop, and unlike other organs, it has to be functional throughout development, and so on and so on. And this makes sense because in a developing embryo inside of you, when the heart starts beating, it has to beat something, and that something has to be blood, and that blood has to circulate through the blood vessels. So it makes sense that the vascular system has to be functioning for the primary first organ in the developing embryo. And so a hemangioblast is the last term we're going to review in order to sort of conclude this whole thing. And it sounds really weird, but you can sort of think of a hemangioblast similar to how we think of our ancestors. So we should all know that over time evolution, we come from one common ancestor, and that one common ancestor eventually branched out through evolution into different types of species. And so similarly, a hemangioblast is that common ancestor, or is a common precursor cell where blood cells and blood vessels derive from. So blood cells and blood vessels derive from the same common ancestor, common precursor cell, which is a hemangioblast. And to be more specific, if this is your common precursor cell, or your common ancestor, then it gives rise to a blood cell, also known as a hematopoietic cell, I believe that's how you pronounce it, and a blood vessel, or an angioblast. So an angioblast is another precursor cell, to get this, endothelial stem cells. And what are endothelial stem cells again? They're the first layer of the blood vessels that are found that are used to create angiogenesis, which is the development of new blood vessels. So this is how everything forms from that one cell in embryonic development. And so one really cool thing that I think was taken from Sherry Shkoplar on YouTube was this quite little animation of how everything comes together. So here you have your yolk sac endoderm, which is essentially what provides nutrients to a developing embryo. So inside that, you have something called mesodermal cells, which are essentially hemangioblasts. And so these hemangioblasts, remember, are the common precursor cells in a developing embryo. And so they start to form something called a blood island, where they group together. And as you can see, the cells in the blood island begin to differentiate. And this is where vasculogenesis happens. And remember that vasculogenesis is the differentiation between blood cells and blood vessels. So when they start to differentiate, you'll see that hemangioblasts on the outside of the blood form angioblasts, which remember are the precursors to endothelial cells, which are the precursors to the walls of the blood vessel. And so the red cells on the inside are hematopoietic cells, which remember are the precursors to blood cells. And so when everything forms, you'll see that they start forming and they start to differentiate and move into place. And eventually those endothelial stem cells will start to form in between the first layer of the blood vessel. And finally, you have your very first blood vessel inside an embryo. So with this being said, the big concept I want to get out of here is that I've been doing research for 2 months. I've asked all my science teachers this question. I've asked my uncle, who's an anesthesiologist, the same question. And during our senior field trip to the Human Body Museum, I've asked 3 of the doctors that were working there the same question, and I've gotten different answers from each one of them. Whether that be the blood vessels came first because it needs to branch out before the blood comes, or the blood came first because the heart has to pump the blood. And then after prompting them with several more questions, they sort of became baffled, like, I don't really know what it is. So because this is such an ambiguous and open-minded question, I had to take it upon myself to create my own hypothesis for my senior driving question. So if you're going to ask me, Lolita, which came first, the blood or the blood vessels? I would say none did, because they developed at the same time. Over the past 2 months, I've conducted research, gathered as much evidence as I can, became confused for a long period of time because of all the words that I had to know, because of every type of structure and what people were telling me. I had to digest all that and create my own hypothesis. And so this is my answer. They came at the same time. So as I'm entering into the major of biology next year at Humboldt State University, I think that I definitely pushed myself a lot more than I needed to here, but I think it's a good thing in a way, because embryonic development and fetal development is something that we didn't get to cover a lot at Da Vinci. So pushing myself to the limit to learn and go beyond what I needed to know, I think will definitely help me when I'm entering my major in college in biology. And I genuinely think that the human body is a great phenomenon. There are some things in the human body that still can't be answered today, and I think that right now, me delving into this question that not even a lot of people can answer was just a great further step in my research for this project. So, my name is Lolita. Let's end this talk.